So, good morning, and today I want to talk primarily about further logical constructs, basically all of predicate logic, and then proof methods that go beyond simp and auto. So, first I'll talk about logical formulas, then about proof automation, and finally, because not everything is automatic, we will also learn how to perform single-step proofs where you slowly move towards the proof of the goal. So first, logical formulas. Well, the language of logical formulas is fairly standard. So it uses the mathematical symbols that you know, like parentheses, equality, negation sign, conjunction, disjunction, implication, and then universal and existential quantifiers. And the only thing, there are a few syntactic things that I need to point out to you. So here are some examples, and they also demonstrate that the syntax here I'm showing you is enumerated in decreasing precedence. That means equality binds very tightly, negation binds a bit less tightly, but and binds more tightly than or, and so on. So if you write this formula here according to the sequence of alternatives in the grammar above, the not binds most strongly, so it's the parentheses are around the not then the and binds more strongly than the or, so their parentheses are around the not implicitly, and then finally the or is on the outside. Here is another one to demonstrate that equality binds more tightly than conjunction. So if you write S equals T and C, the S equal T is regarded as one formula, and then comes the and C. But on the other hand, notice that equality is also defined on Booleans, so that if you write this formula, A and B equals B and A, and as the form of the formula suggests, you might want to express, or you might think you have expressed some sort of commutativity property of and, but it's not like that. The equality binds most strongly, so what you've expressed is a conjunction of three formulas A and B equals B and A. So you have to be careful when you use equality on the Boolean level, because it binds strongly, whereas the if and only if on a Boolean level is you naturally assume to bind weakly. And finally, the quantifiers, their scope extends as far to the right as possible. So here the universal quantifier binds all the way to the end of the formula. And if you do want, you can also use the if and only if symbol rather than equality on the Boolean level, and then the precedence is the same as the implication. So if you look at the table up there, it's a rather weak precedence. You can also abbreviate nested variable bindings like this. So if you have a quantifier and then you want to bind a number of variables, you can write it without repeating the quantifier. You can just write for all x, y, and then comes the dot. And that's just the same as having written two quantifiers. And that works also for other variable binding constructs like the existential quantifier and the lambda. And here a word of warning where the syntax differs from conventional syntax. The quantifier, just like an if then else and a case, needs to be enclosed in parentheses, otherwise the parser will complain. So that on the left one is not a good idea, the one on the right is the correct one. And the motivation is again that the quantifier, there's no obvious construct that closes the quantifier, the quantification, and therefore you have to put the parentheses around it to delimit the scope of the quantifier. Here's a table which I don't want to go through, but how do we input these symbols? Well, there are various ways of inputting these symbols, including, of course, the table that you can get. There's a symbols table in the JEdit interface, and you can also select the symbols from that. Right, sets we had already briefly used last time. Let me just go over it again. So sets over a type A are written A set as a type, and they have the usual syntax, well, almost the usual syntax. The empty set is just written open brace, close brace, and if you enumerate any set, you write it in the conventional manner by enclosing the elements in braces and separating them with commas. Then you have an element operator, a subset operator, union, intersection, set difference. Minus A is the complement of a set. And there's also set comprehension, which is written with a dot rather than a vertical bar. So the set of all x such that P, that is what this means. Now, the only reason why we chose a dot rather than a vertical bar is that to emphasize the similarity to other variable binding constructs like an existential quantifier, the quantifiers or the lambda, where you always use the dot to separate the bound variable from the formula. And so it's just the similarity with these other constructs that that's why we chose the dot. And there is lots more, but we won't need lots more. I think we will get along just fine with these basic operations. And of course, there's again a question of inputting them. And down here, you see the ASCII equivalents for the most important ones. Right. That was all about logical formulas because it's very close to what you're used to, except for a number of syntactic specialities. So now I want to move on to proof automation, and I want to discuss a number of further proof methods and their strengths and weaknesses. So remember, so far we had simp and auto, and what does simp do? It just does rewriting essentially and a bit of arithmetic, and auto does a bit more. It does rewriting, also arithmetic, but it also knows to some extent about sets and logic, but not that much. And the main advantage of these two methods is that because they don't try too much, they show you where they got stuck, and then you can take a hint from that and can say, oh yeah, they got stuck because they couldn't simplify a certain subterm, and then that leads you to the discovery of a new lemma. But they are highly incomplete. So that's the trade-off you have here. And now I will discuss some more proof methods that are typically, they don't show you where they got stuck, they just fail. On the other hand, they are more complete. And yeah, both of them are extensible with new simp rules. And there's this little exception. Auto is the only of the proof methods, the only one of the proof methods that acts on all the subcodes rather than on just the first one. So one level up is something called fast force, and it seems to do the same thing as auto, but the difference is that it's still incomplete, but it's significantly better than auto. But the drawback is it only succeeds or fails. So if it fails, it doesn't tell you why it failed. It just didn't work. And that doesn't really give you much of a hint what to do now. And it's also extensible with new simp rules like simp and auto are. Then there is BLAST. That is actually, in principle, a complete proof search procedure for first-order logic. I'm saying in principle because in the implementation there's a depth limit and it doesn't go on forever, but if it hits the depth limit, it'll stop. But in principle, the algorithm behind it is complete for first-order logic. The big drawback here is that the proof search procedure knows almost nothing about equality. So it's basically very complementary to simp and auto that use equality very much, but don't know that much about the other logical operators. And this BLAST method is excellent when it's just a question of logic and sets, but it's not so good if there's much equality in there. So this is really its strength of logic, sets, and relations. But again, it just fails and doesn't tell you why it fails, because it's trying such a huge number of alternatives. There's no nice way of saying this is why I failed, because you could say, oh, I tried this 100,000 alternatives and neither of them worked, but that is not going to be helpful for you. So and it's also extensible to some degree. And finally, there's something, again, complementary in the sense that all the previous methods, they know about some fixed set of rules, like rules for logic and rules for relations and things like that. But if you have your own theory of something, they won't know about that theory, and they will not be able to apply rules from that theory automatically, except, of course, auto that use the simplification rules automatically. Sledgehammer is the other way around. Sledgehammer knows basically the complete background theory and tries to use as much as possible from that. Now, Sledgehammer is, in fact, much of why Sledgehammer is so powerful is not due to Isabelle, but due to external automated theorem provers. So Sledgehammer is an architecture that links Isabelle with external proof procedures. And how does this work? Isabelle sends to these external automated theorem provers the goal that it's trying to prove and a filtered form of the library. Why filtered? Because the library, if you're in main, you have like something, probably at least 6,000 lemmas in the background library. If you throw all of those into the external automated theorem provers, they're not going to get very far because it's just too many. So Isabelle will filter the ones that seem promising and will only pass those to the ATP. And then the ATP do their job, and if you're lucky, they return a proof of some form. And that proof will then be recast in an Isabelle method call, and that's what you then can paste into your theory. So in the end, the proof that you get is actually run in Isabelle. It's just that Isabelle got help from the external provers to produce that proof. But we're not relying on the soundness of the external provers because the proofs are always replayed in Isabelle. So that's the general architecture. And, well, the characteristics with all these automatic theorem provers, sometimes it works and sometimes it doesn't. So you just got to ask yourself one question: do you feel lucky? And usually, when you don't know, when you don't have a better idea, you always try Sledgehammer, but don't overestimate it. It's good at filling little gaps, possibly with lemmas that you've never heard of that are in this huge background library, but it's not going to make huge steps. It's just you need to try it and see what it's good at and what it's not good at. And this is just a little side remark. In the examples that you see, I will frequently write by and then some proof method, and that's just a shorthand for writing apply the proof method and then saying, oh, well, actually, it's done. So by means I'm apply this proof method and it should really finish that proof. As opposed to if you say apply auto, then you're prepared for something being left. But if you say by auto, then you're saying, well, there should nothing be left anymore. Yes, automating arithmetic, that's a separate topic. I think I would first want to demonstrate what we've seen so far in the demo file, and then we come back to the automating the arithmetic part. Where are we? Yes. So here we have the demo file. And here are just some simple examples of logical formulas that can be proved automatically by Auto. So Auto does know a little bit about logic and sets. So it can, for example, prove that for all x there exists a y such that x equals y. That's not terribly exciting. The next one is a little bit more interesting, but not too exciting either. If A is a subset of the intersection of B and C, then A is also a subset of the union of B and C. So Auto can prove that one as well, but there are limits. So here, for example, there's a theorem that Auto will not be able to prove, and note the bounded quantification that we also introduced last time already. So this, what does this theorem say? It says every list x's in A, for every list x's in A, there exists a list y's such that x's is of the form y's append y's. So every list in A's is claimed to be of the form that it's two lists, twice the same list behind each other. And then there's a second assumption that US is an element of A, and then the claim is there exists an n such that the length of US is n plus n. Fairly obvious. Fast force can do this, Auto can't. So it's just to show you that there are boundaries where some of the proof methods will jump over and others won't. Now, if you are wondering, do I have to try all of them? First try Auto, and if that doesn't work, try Fast Force. There is a little trick here, or rather a little useful command. You can type try 0, and then it'll try a range of basic proof methods, and it'll then tell you which of them succeeded, and will suggest that you should try this one. So this is quite helpful. On the other hand, please note, it will only try the proof methods in an unparameterized fashion. So if you want to add further simplification rules, it won't do that. It'll just try the proof method Fast Force or Simp or Auto. So that means it's limited in its capacity. On the other hand, it's not a bad idea to try that first and see if there's some obvious proof method that can prove it. So here indeed. Oh yes, and what I should have shown, let me go back there. So after it's found a proof, what you can do, it'll display the proof, and that you can see that it's, well, now it looks green, but before it was gray. If you see such a field, then you can click on it. Oops. Click on it, and it'll transport it up into the upper window. So you don't need to cut and paste, but you can just click on it. Okay. Now, the next one is one of those theorems that if you think about it for a time, it becomes quite obvious, but the first time you see it, it's not obvious. So what is this? If you recast this theorem in natural language, then you would say if T is a total relation and A is an antisymmetric relation and T is a subset of A, then A is a subset of T. You may or may not immediately see why this is the case. I've now written this out in logic. So the first line says T is a total relation for all xy, either txy or tyx. Next line is the antisymmetry of A. If A holds for x and y, and A holds for y and x, then x must be equal to y. And the next line, the third line, is that T is contained in A, except I'm not using the set theoretic containment, but I'm writing it as an implication. If T is true for the elements xy, then A must also be true for the elements xy. And now the final line is the claim that then A is also a subset of T, A subset T. And this is something that BLAST, for example, can deal with very nicely, because there's practically very little equality involved. I don't know about the other proof procedures. If you now try 0 here, it says here it shows you at the bottom, a lot of them could solve it, but BLAST was the one that solved it in the least time. That's why the system is suggesting to use BLAST. But Auto, for example, it's not showing, so probably Auto didn't solve it. And then finally, Sledgehammer. And here's an example of a theory that is not built into any of the standard tools like Auto and FastForce. That's the theory of relations, obviously, but in particular the transitive closure, the reflexive transitive closure of a relation. That's what this arrow means. And so here the theorem says that the reflexive transitive closure of R is a subset of the reflexive transitive closure of R union S. This is perfectly obvious. Why? Because the reflexive transitive closure is a monotone operation. If you have a bigger relation you start with, then its reflexive transitive closure will be bigger. And so then, therefore, because R union S is a subset of R, it must the transitive closures must also be subsets of each other. But if you were to prove this by hand, you would now have to go back, where is this thing defined? You can click on it, and then you, oops, why isn't it taking me there? Then you're taken to the theory transitive closure, which is part of main, and then there is an amazing amount of material in there, and you'd have to search through it, maybe using the search facility, but still this could take you something like 5 minutes or to find the right lemmas. So why don't we ask Sledgehammer? And so you click down there on the Sledgehammer panel, and then you can click on apply, and it'll then very quickly, this is unusual because it's so simple, it'll find a proof, and it'll list down here all the external proof procedures or proof systems that found the respective proof. So Z3 is an important one, and it found a proof that when replayed in Isabelle takes this shape. Now, of course, Z3 doesn't know anything about SIMP, but it gave the information back that this lemma R truncal mono, the monotonicity of reflexive transitive closure, that this lemma is part of the overall proof, and then Isabelle managed to reconstruct it and turn it into this nice SIMP call. So if you now click on this one, yep, it'll just do it. But as I said, it's not always as simple as that. So for example, let's make this, I don't know, R, let's make it S union R is subset R union S star, which is still pretty obvious. But if we now ask Sledgehammer, oh, okay. Actually, it still found a simple proof. I wanted to have something more difficult. We could also iterate the star. I wonder if that makes it any more difficult. If we take the star twice, but then we need to put the parentheses in. And now ask Sledgehammer. No, it's still amazingly simple. So I can't think of any difficult proofs here, but we'll find some later. Oops. In fact, why don't we try this one? First, you suggest some property P such that this implication is true, and then I will ask Sledgehammer to prove it. So this is an equality between lists, which tells you basically that you have on one side a list that starts with A, on the other side you have a list that ends in A, and what does that tell you? How are X's and Y's related?
Well, both contain A, which is really good.
So you're saying both X's and Y's contain A?
No, the whole terms on both sides.
Yes, that is trivial indeed. Yeah. So,
But the other, isn't it a palindrome?
pardon?
Isn't it a palindrome?
Let's try that. But there are two lists here. So you're saying, what is a palindrome?
I'm not sure how to formulate it in logic, so maybe.
Yeah, but just in language, you're saying it is a palindrome, but what is a palindrome?
So that's where you have one string.
No, I know what a palindrome is. I'm asking you, which of these things in there is X a palindrome?
I was thinking that you were sort of building a palindrome using x's and y's.
Yeah, but that's a bit vague. You can build a palindrome using X's and Y's. So you have to be a bit more precise than that. That's not just vague formally, but also informally. So, but other people are welcome to join in and suggest something. Yeah?
It exists Z such as X's equals Z.
Such that, sorry? Such that?
Such as X's equals Z at A and Y equals A.
That is?
Yes.
Mm-hmm. Sounds reasonable. Now, for such a simple proposition, it's taking a long time. It'll take up to half an hour, up to half a minute, then it'll time out. So I'm already suspecting this isn't true, what you're claiming. The problem is we're not, quick check isn't giving us a counterexample because there's an existential quantifier in it, and that's difficult to deal with automatically. So they didn't find this. So maybe somebody in the audience can find a counterexample. I think it should be, it's probably false, but yes, it's false. I have a counterexample. For a very specific value of x's and y's, it's false. Yeah.
I think if they both are the emptiness.
Yes. So maybe we can put it with an implication saying they're non-empty. Or we could say either they're empty or this thing exists. Let's try that. Either x's is empty and y's is empty, or this existential statement is true. So now let's ask Setschimmer. Now it found a proof. So you were almost right. You just forgot the boundary case. And now it finds a less standard proof, less standard in the sense that you've never heard of metis. That's the proof procedure is metis, and then the list of arguments is a list of lemmas that it found in the library that, if you put them together, imply the proposition. And metis is simply a very weak automated theorem prover that's inside Isabelle, but it's strong enough to replay many of the proofs that the automated theorem provers can find once it knows that it only needs to use these 3, 4, 5 lemmas. Then it can often reproduce the proof. It's the difficulty that the automated theorem provers are solving for us is which of the maybe 500 lemmas that seem reasonable are the actual ones that will get us to the goal. And once you know it's these 3, then it's very easy to replay the proof. And that's what Mattis is doing. And so if we move that up there, then it's done, the proof. Of course, we don't need the oops anymore because we've now proved it. But let me remove this so the file stays intact. Yes. So this is what I wanted to demonstrate for you. So Sledgehammer is particularly good if you're dealing with some library of things that you don't know much about. I mean, you don't know all the individual theorems in there, but you're not expecting it to be a difficult proof that takes lots of steps to get to. So Sledgehammer is good at combining all the relevant facts if the relevant facts are already there. Okay. So, oops, I wanted to get there. So that was the first part. Now, automating arithmetic is a special situation because arithmetic, well, mathematicians have been thinking about arithmetic for many hundreds of years, so they have developed their own methods of how to solve certain classes of formulas, and some of these methods are actually embodied in Isabelle. But yeah, let me walk you through that. And a class of formulas that is quite widespread and that can actually be dealt with automatically are the linear formulas. So what does a linear formula mean? Essentially, it means no multiplication. It's not quite like that. It's a bit more, but think of it, linear means no multiplication. So what do we have? We have variables and numbers. We are allowed to multiply a number with a variable, but not a variable with a variable. So we are allowed to have 2x, but not x squared. We're also allowed to have addition and subtraction and the usual arithmetic comparisons. So those are considered linear formulas. And you then may even combine those basic linear formulas with the usual connectives like and or, and implies and negation. So here are some examples. So this is a linear formula. There is multiplication in there, but only multiplication with a constant, and everything else is just addition and then the logical operators and the usual comparison operators. This, on the other hand, is not linear. Now, in fact, you can extend the linear formulas, I'll call them extended linear formulas, with a number of further operators like min and max, even and odd, and also even diff and mod, but just like with multiplication, only in a very restrictive sense, namely you can write some term diff n, but then n must be some concrete number like 2 or 3. If you write something where n is really a variable, that's no longer a linear formula. And you can also have the conversion functions that embed the natural numbers into the integers or into the reals. And you can even have some of the conversion functions in the opposite direction, like the floor and ceiling function that take a real number to an integer. So this is quite a rich set of formulas. And this set of formulas can, in fact, be proved automatically by a proof method called arith. So it tries to prove arithmetic formulas in general, and it succeeds or fails, and it's actually a decision procedure for extended linear formulas. But that means it's really only arithmetic. If you have other stuff in there, like you have another formula in there that says something about lists, you can try arith on it, but it will just ignore that part of the formula. And so if it has anything to do with the correctness of the formula, it will just not be able to do much about it. And what it does, anything that's non-linear will just be replaced by a new variable. So if you give it a formula like this, x is less or equal x times x plus f of y, then it just says, oh, I have no idea what this multiplication thing is, I'll just replace it by u, and I have no idea what this function f is, I'll replace it by v, and then it'll try to prove that x is less than u plus v, which is most likely not going to be provable, because u and v are new variables that you don't know anything about. Whereas this formula may actually be provable if you know, for example, that f is always positive or something like that. So it can sometimes work even if you have proper multiplication in there, but most of the times it then won't. Now, this is nice when it works, but when it doesn't work, there are still some things you can do. Namely, a very heuristic approach is to use a background set of simplification rules called algebra simps. So this is something that we have put together to help you prove things in general about algebraic structures, and in particular about numbers, because these numbers, of course, also form algebraic structures like rings and fields. And so if you add explicitly this collection of rules, what will that help you? It'll help you to simplify arithmetic formulas. Well, that doesn't necessarily mean they really become simpler, but they are moved into a more canonical form. And that means, in particular, it will use, so there are other rules in there as well, but in particular those three here, associativity, commutativity, and distributivity of addition over multiplication. So that means if you use distributivity, of course, the thing can blow up. But at least then it becomes more, the nesting is all gone, and it's a more canonical form that you move it into. So this can be helpful using algebra sims. It can also make the formula completely unreadable. You just have to try. And in particular, if you're in a situation where maybe you have a formula that you're trying to prove s equals t, and s and t are almost the same, except that some arguments are permuted, an argument of a plus or a times, then this is you stand a good chance of proving it. Yeah. So there are these three alternatives, and you just have to try and see what happens. And you can also simplify formulas not just about rings, but also, so algebra sims basically goes up to rings, but that means you don't have any inverse operation for the multiplication. You have no division. If you also have division, then you can ask to simplify with respect to field sims, which is a more extended set of simplification rules. But there you get into one problem, namely, if you try to simplify a division, you always have to prove that the denominator is non-zero. And so that could be tricky, and therefore this is not very complete. It'll try to prove that the denominators are non-zero before using some simplification rule, but if it fails, it just can't use that simplification rule. And yes, here's another example. You can cancel common subterms, but only if that common subterm is non-zero. If it's zero, then you can't cancel it. And so therefore, it'll try and prove non-zero-ness of certain subterms, but it may not succeed. So all of these are heuristic approaches, except that you can actually show that, for example, algebra sims is complete for rings. So if you have a free ring, then this will give you a decision procedure, but that's just a very special case. And finally, you may get into a situation where you have to deal with numerals, and note that numerals are really syntactically different from successor terms. So if you write the numeral 2, it's a different term than if you write successor of 0. And sometimes you may end up getting into a situation where you have both of them in your formula, and you'll have to turn one to the other, and therefore So, for example, yes, numerals do not match successor patterns. If you write, for example, factorial of 2, it'll just stay there, factorial of 2. If you write factorial of successor of 0 and simplify it, it'll get evaluated. But not with the 2, because the factorial function is defined with successor, and if you have the numeral 2 in there, it's not a successor term, and therefore it doesn't work. So sometimes you have to convert numerals into successor terms, and this is the other example I use. Exponentiation is defined by recursion on n with successor. So if you write x to the 2 and simplify it, it just stays there because 2 is not successor of something. And you can convert numerals into successor terms by adding the simplification rule numeral eq sub. So that's something you may have to do in some situations. So this is really a very just a very special case, but you may run into it, and therefore I've listed it here. Yeah, and so what happens if you write sim add numeral and you start with that term, it'll really get rewritten to x times x. Now let's look at some of the examples. No. There we are. I thought there we are. No. There. So the first one, the first formula down here, that's just an example of a linear formula. And note that I added a type annotation and said that a is an integer. If I don't do that, if I remove this, then it won't be provable anymore, because now the type that we're talking about is completely open. It could be anything, and then you can't use linear arithmetic because it's not even clear that this is arithmetic. This might be some arbitrary type that has addition and multiplication. And so if I add this annotation, then it's clear that a is an int, and by consequence, then basically everything in there must be an int. And here is also an example where, if you're lucky, it can also deal with some unknown function symbol like this f here. So it means that since it could prove this, it's completely irrelevant what f really is. And why is this? So how do we get from the premises to the conclusion? Yes. How would you do it by hand? How would you get from the premises to the conclusion? You have to combine the two premises somehow. If you manipulate the first less or equal a little bit, then it becomes quite clear what's happening. Yeah.
So I would have modified the less.
You want to modify this one, the second one?
Yes, you could do successor and then less.
Yeah, but that alone doesn't help. That is part of it. Yeah. Okay.
Substituted the formulas on the right. So I would have inserted
Hang on, what do you mean? You can rewrite this as less or equal and then plus 1 on the right-hand side, okay? Or the left-hand side, sorry, yeah.
And now if we then substitute C and A on the right side with those formulas, the two assumptions.
But what kind of trick are you playing there? So how, if I rewrite this, that's perfectly okay. Yes, that's the same thing. But how do you now combine these two? You want to substitute what for what?
On the conclusion side,
Yes.
I would substitute A for fx plus b.
But
And this would be
you want
then be strong.
you want to replace this A by this one.
Yeah.
Okay. Yes, you can do that.
And then the C by the other two fx plus 1 on the right side. And then it still holds, so the original conclusion is true.
I don't think that's valid what you're doing. You're starting out with what you're trying to prove, and then you manipulate that until it's something that's true. So it may be true, but I find something. So I'm not saying this is really wrong, but let's do something else. That was fine. How about multiplying the first inequation by 2 and then adding the two inequations? So I think that's, I find that more in a more goal-directed manner, yeah. So then you have 2a less or equal to f of x plus 2b, and you add it to this one. Then you have the 2f of x on both sides. You can cancel them, and then you have 2a plus 1 less or equal to b plus c, yeah. So, but I think it just shows that it's not so easy, even with linear formulas. It can easily take you some 5 minutes to really properly write this down, and it's very nice if some decision procedure can do it for you automatically. And here's another cute one that shows you that even with quantifiers, this decision procedure works. So this says for all numbers greater or equal 8, there exists, and now we're talking natural numbers here everywhere, so there exists I and j such that k is the linear combination of I and j and multiplied with 3 and multiplied with 5. And so this is often stated as the stamp problem, that any value greater than or equal 8 cents can be gotten as a combination of 3 cent and 5 cent stamps. And so this can be done automatically. Where it can't be done automatically, if you now, if you were to modify the 3 and the 5 and make them variables, and then that wouldn't be linear anymore, and then it can't be done automatically. But this one can be. And here's a simple example that even with mod, some things are automatic provided the second argument of the mod is a constant. So what does it say? N mod 2 is 1, then n plus n mod 2 is 0. Yeah. Because it's if the sum of two odd numbers is an even number. Yeah. And finally, it's an example of something where if you tried arithmetic, for example, you could say by arith here, it will fail. Why? Because if you look at the formula, it's a nonlinear formula. X plus I plus j times I minus j is the same as I times I plus j times j. In fact, it's a less than or equal. Why isn't? Oh, yeah, it's not an equal. Sorry, yes, it's a less than or equal. And this just doesn't work automatically by arithmetic, but it works automatically with algebra simps, because if you multiply out the left-hand side, you get I plus I, and you get what is the word? I plus j I minus y. You get the I squared, but then you get minus j. Oh yeah, you get minus j squared, but on the other hand, you have here plus j squared, so it's bigger. And then the I plus j and the j, the other cancel out. The other two expressions cancel out. So it is really the case. It's not a very deep theorem, but it's one. And if you of course try to prove something like this, it'll probably just get stuck. Oh no, that's also true. Oh yeah, because the j squared that you're subtracting is
They're squared, so they're always positive.
yes. I'm surprised it knew that. Yeah. But if you write plus u, then it won't prove it anymore. But you can still see what was left over. It couldn't. I mean, that's where it got stuck. 0 should be less or equals u plus j times j. And if you don't know anything about u, then you can't prove that. You look, yeah?
I just have a question about the fixes ij.
Oh, right. I haven't introduced that syntax yet. Sorry. Yes. So this is a bit of syntax that I should probably not use at this point. So I'll replace it and put it inside and say this is an int and j is also an int. And then you can delete all of this. But it's it'll come in 10 minutes or so, but I shouldn't have used it here. And finally, an example where you just use the simplifier to evaluate something, for example, that 5 squared is equal to 20 plus 5, and then the simplifier will just do that. Yeah. Because everything, because yeah, because everything here is a number, I mean a concrete number. That's why I can evaluate it. So we have taken care to make sure that all the basic operations, if all their arguments are numbers, then simplification will evaluate them to a number again. That's why it works. Okay. Then I would like to start on the single-step proofs. So yes, automation is great, but if automation fails, in particular, if even sim or auto don't leave you anything unproved that's helpful, but you're just stuck, then you basically have to try and dig into your formula by hand and decompose it into smaller subproblems. And this is where the single-step proofs are helpful. So first, a little explanation of something that you've seen but I've never talked about, these question mark variables. Where do they come from? Well, it's as a matter of principle, when you state your theorem and there are no question mark variables in there, but after you've proved it, what Isabel will do is the actual theorem that is then stored and will be displayed when you ask for it, will have all the variables replaced by question mark variables. So what are these things? Well, so here's just an example of a theorem of this form. If you ask what is conj I, which stands for conjunction introduction, we'll get to it in a moment, then it'll say it's this theorem here that says that under the assumption of P and Q, you can prove P and Q. So here you have P and Q with these question marks in front of them, and logically they are just free variables, but operationally the system knows it's okay to instantiate these free variables by arbitrary values. So this is what the question mark says. It says, you can give me some instantiation, you can give me some term, and then I can replace that question mark variable by that term. So it's just another way of expressing that these question mark variables are universally quantified, and this substitution business is just instantiating the universal quantifier, but you don't see the universal quantifier, instead you see these question marks. And how do you instantiate them? Well, you can do this by hand, and we will frequently do this in order to specialize theorems. So here we're specializing the theorem conjunction introduction, which is that theorem up there, and this is the format such a specialization or instantiation takes. This is the operator, so it's a bit of an unusual syntax. So it says, take the conjunction introduction rule and now specialize it, instantiate it with these two formulas. So now the question arises, there are these two question mark variables, P and Q, which one is substituted by which of those two formulas? And here the rule is simply that you go through the theorem that you're instantiating from left to right and instantiate the variables as you encounter them in this left to right traversal. So that means A equals B is substituted for P, and false is substituted for Q, just because you've met them in that order when you go through the term from left to right. And so that means this is the theorem that you get as a specialization of this theorem, where now the two question mark variables which stood for formulas have been replaced by concrete formulas A and B and false. So this may not appear to be very helpful, but this is just a simple example. And so what we will sometimes use this for, like you have some, say, some arithmetic formula, and you want to use it in a certain context, and none of the automatic proof methods find the instantiation needed, then you take that formula and you give the instantiation by hand, and then often the automatic proof methods can take over. But you have to say, oh, in this theorem here, please put in the number 3 and the term x plus 1 for these two variables. Yeah.
My question is, can this be used to provide a counterexample if we want to prove something?
No, because you're always starting with a theorem, so that is definitely something that's true. So by instantiating it, it won't become false. So I mean, I'm not sure. Maybe in some way it can be used, but I'm just saying these are the limitations you have to face.
Unless you're not usually used to this.
No. It's really used to get a specific instance of a general theorem where the proof methods typically may not find that specific instance, and you'll have to give them some help. That's what it's mostly used for. Now, the second way is automatically as part of some proof methods. So you won't be doing that by hand, but it happens under the hood. And namely, by unification. What does unification mean? It simply means you have two terms and you want to make them the same. And in the process, you will have to instantiate some variables. So here, for example, if you want to unify this formula with this formula, well, you have to instantiate P with A equals B, and you have to instantiate Q with false. That's the only way to make them identical. And this is what unification does. So here you have given this instantiation by hand. Here it was computed from this attempt to make two things the same. Now, where does unification kick in? Well, that's part of something bigger, and that comes on the next slide. So all this slide says is you can use it by hand with this little off operator, or you can use it as part of more powerful proof methods that provide unification. And yeah, so this is what I just said. And the most basic of those is rule application. What do I mean by rule application? I really mean backwards rule application. You're trying to prove something, and then you have a rule that unifies with what you're trying to prove, or rather the conclusion of that rule unifies with what you're trying to prove, and then you can say, oh, I can use that rule backwards. That is, if I can prove all the premises of that rule, then I've got the thing that I wanted to prove. And so that's what I mean by rule application. And the example that we're using is the conjunction introduction rule. And assume we are in some situation where we have a sub-goal with possibly many assumptions, and the sub-goal is that you have to prove A and B for some concrete A and B. And then you can say, oh, I can do this by using conjunction introduction backwards. That is, by unifying the conclusion of this rule with the current proof state, and then replacing that current proof state with two sub-goals, namely proving P and Q separately. And this, somebody in one of the earlier lectures asked, is this like prologue? Yes, this is like prologue. If you know prologue, this is just using one of the clauses backwards. And so the result would be that you have to prove A and you have to prove B. And how does that work sort of in detail? If you, or in general, if you are trying to apply a rule of such a form with some assumptions, A1 to AN and the conclusion A, to a sub-goal that is where you're trying to prove some C under some assumptions, what you do when you apply this rule, it means you first have to unify the conclusion of this rule with the with what you're trying to prove, the sub-goal, but not with the assumptions, just with the conclusion of the sub-goal. And then you replace this one sub-goal C with n new sub-goals, namely the assumptions of the rule that you're using. And this is how you write it. Now, what I'm writing here, replace C with n new sub-goals A1 to AN, isn't quite accurate, because in the unification process where you unify the conclusion A with the sub-goal C, that will also instantiate the variables that appear in this rule. And then you're not replacing C with just the original A1 to AN, but of course with the instantiated A1 to AN. So if you go up here, in this situation, the unification process of P and Q and A and B means that the P is set to A and the Q is set to B, and then you don't replace the original subgoal A and B with P and Q, but you replace it with A and B because they have been, the P has become A and the Q has become B. So that's why this isn't quite accurate, but it's accurate enough. And this is a way to just use rules in a single-step fashion, use one rule at a time and see how the goal develops. And here in this situation, for example, maybe after you've applied the conjunction introduction rule, you've got now two subgoals A and B, and now maybe you find that A can be solved automatically, and then you know, oh, the difficulty is really in the B part. So that's why this is helpful, to decompose what you're trying to prove. And this is often called back-chaining with these rules, because you're going from the conclusion of the rule backwards to the premises. And these are typical backward rules if you're trying to decompose some proof goal. Here's the conjunction introduction. Here's the implication introduction. So that means if you try to prove something with the implication of the whole system, if you use this rule backwards, it's replaced with an implication that's part of the framework. That's the framework implication. And that means at this point, this is really an assumption, and this is the thing that you're really trying to prove. Whereas here you're in a situation where you're trying to prove this whole thing unconditionally. Similarly, for the quantifier introduction, if you're trying to prove for all x p of x, well, this rule tells you that you can prove this if you can prove p of x under this other quantifier, this other universal quantifier, but this is one that's part of the framework, and therefore, when the system looks at a formula like this, it's saying, oh, I'm really trying to prove P here, and this is just a comment saying, oh, and the X here is a constant in that proof. Whereas here, you're trying to prove a big formula with a quantifier in front. So again, you're removing part of the formula and moving it, in this case, into the context, and you can then concentrate on proving just the P without any quantifier getting in the way. And here's the third one, which can be useful if you're trying to prove an equality between two formulas. Then, if you use this rule backwards, you'll have to prove two implications. One where you assume the left-hand side and you prove the right, and one you assume the right-hand side and you have to prove the left. So these are introduction rules that, if you use them backwards, of course, don't introduce the connective, but they remove the connective if you go from the conclusion back to the premises. Now, this is backward proof. You can also, in a limited fashion, do forward proof, and this is an operator called OFF. So what is forward proof? Forward proof is meaning combining two theorems where the conclusion of one theorem unifies with the premise of the next theorem. So you're making kind of a chain, a reasoning chain there. So assume you have a theorem of the form A implies B, where A and B may be bigger formulas, and assume S, so R is this theorem here, this implication, and S is another theorem that unifies with A, with the premise of the rule. Then you can make the step where here, so S basically says I have some variant of A, and R says, oh, from A you can go to B, and therefore if you combine S and R, you can get B unconditionally. So if you write this expression here, you use this rule and you're trying to prove the first premise of this rule with our fact S. So S is just a theorem that unifies with A, so it unifies with the premise of the rule, and therefore the whole thing should be something like B, except that it may be an instance of B, because A and B may contain variables, and when you unify the theorem S with A, some variables will get instantiated, and therefore you don't get B as it was originally, but you get an instantiated version of B. Here's a simple example. REFL is the theorem S here, so it's a theorem that contains variables that says every term is equal to itself. And then we have, that was too quick, we have our well-known conjunction introduction, and so the question is, what is the result of this thing? What's the result of the inner expression, REFL of A? With a little of. A equals A. And what happens now if you try and use conjunction introduction on that fact? So let's just recall what is conjunction introduction. It looks like this, and I now put in all the parentheses. So this is what it looks like. Can you just move this out of the shadow? It's probably better. So this is our rule R. And our S is just the fact that A equals A. So what we're doing now, we are saying, oh, let's unify this fact with the premise of the rule, which is just P. So the result will be that in this rule, P is instantiated, but also P has been proved, because this is a proved fact that A is equal to A. So from that, you get what is left here after you've gotten rid of P. So in the end, you just should have, and now we don't need parentheses, the Q hasn't been instantiated, but the P has been instantiated. That's the result of R capital of S. And so you should really think of R as a rule. You should think of the rule as a function that if you give it a proof of A, it gives you back a proof of B. Or if you give it the theorem A, it gives you back the theorem B. And that's what we're doing. We're giving it, well, the premise is completely open, so we're giving it very specific instance, and we're saying, please unify these two, and as a result, I get this one, but instantiated with the A equals A. So this is how we got there. And these two operators, the little of and the big of, do quite different things. The little of just gives you a special version of it, but the A here is just an arbitrary term that you're putting in. Here, the big of really combines two theorems and uses the theorem R here, the first one, as a function that, given the second theorem, produces the conclusion of R. And that's exactly what's happening here. We're moving from the premise that has been proved, well, a very special instance of it has been proved, and then we get the conclusion of it specialized to that instance. So you can think of this of here doing two things in one. You can say, oh, what F does, of first does, the big of, it specializes R and puts in A equals A in this case for the premise. Then you have a big theorem that says if A equals A, that implies P implies A equals A and, Q implies A equals A and Q. At that point, it's still a theorem with another premise, but then you say, oh, hang on, here I have a proof of A equals A. So therefore, this theorem should give me its conclusion. And that's what we get here. And the first step, the instantiation, that's the result of the unification process. And the second step, getting rid of the premise itself, that's a logical inference. If you have A implies B and you have A, then of course you get B. So that's what's happening here. But it's happening in, the two things are happening at once, the instantiation and the step from the premise to the conclusion. And you can generalize this if you don't have a single premise, but you have multiple premises in this general form. If R is a rule with multiple premises, then you can also prove all or some of those premises by some other theorems that you get from somewhere. And then you can write this rule of then rule 1 to rule m, and that just means take this rule and try to prove the first m premises with the rules R1 to Rm. Here we're just trying to prove a single premise with a single rule, and here is the general format. And here's another example of that. So again, our reflexivity theorem. So the question, what is the result of this? Of course, this is A equals A. This is B equals B. So what does it mean if I apply conjunction introduction to the two theorems A equals A and B equals B? Which theorem do I get out of it? Remember, this is now the big of that applies a rule to some facts. And this is the rule.
B equals B, therefore A equals A and
B equals B implies A equals A. Implies
that's B. Hang on, sorry. So we're
Yes.
Right? So Q is replaced with E equals B. Or it's the upper formula. So A equals A, therefore.
Well, you tell me.
So if it's the upper formula.
Yes, it is that upper formula. Yeah,
Okay.
that's one.
So the P is getting replaced with A equals A.
Sorry, P, yes, indeed.
Right. Therefore, so now inside the parentheses should be B equals B. And then therefore A equals A and B equals B. If I got it correctly.
Huh?
If I got it correctly.
You didn't, but you got it kind of correctly, but not, it's not the full story. The big off, as I said, is not just making something more specialized. What you've done, you have given us, in fact, this would be the result if I write a little off here. Then, no, in fact, no. What you've done is the following. Conjunction introduction of A equals A and B equals B. But this is just a formula. This is not a fact. This is not a proved thing. You could, in fact, you could have written here A equals Y and B equals Z. And then you would have gotten that same thing, except it would be if A equals Y and B equals Z, then, yeah, same thing. So this, what we've done is something else. We've taken an actual fact that A is equal to A and B is equal to B, and then we have used this as a function to derive some new facts from it, but not this one. That would be far too weak. What is the actual thing?
I think we can remove both the premises, A equals A and B equals B,
Yeah.
so we're left with the right.
So we just have this, because this process that the big off goes through is a two-step process. First, it instantiates the rule like this, but then it says, oh, hang on, I have already proved that A equals A. That's part of the graph of A, so I can remove this. And then it says simply, okay, now I'm using the second rule to remove this, and I'm just left with this. So that's the difference between the little off that simply instantiates some variables with some arbitrary terms, and the big off where you actually use some proved fact to get rid of an assumption. The system will show you these question marks on the slides. I take the liberty to drop them. It just makes the slides a bit more readable. And now let's go through a demo of this. I think the demo is not going to be terribly enlightening. It'll just basically show what we have already seen, but it can't hurt. Yeah, there we are. So here are three instantiation of the conjunction introduction rule. The first one is with A and B, and then you really get just a specialization of the conjunction introduction where instead of the question mark variable, you have the concrete A and B. And by the way, the fact that they are now colored orange in the output alerts you to the fact that you've suddenly invented those out of the blue. The system didn't know about A and B yet, and you've introduced them, and it's just saying, it's just coloring them differently to alert you that maybe you mistyped and you wanted to use something that was already part of this, the context. You can, yeah, then that's another instantiation. That is basically the one that, no, it's not on that slide. Yeah, it wasn't on the board. And you can also not instantiate some part of the formula by just writing an underscore. So here you have instantiated in the line where the cursor currently is, you have instantiated the first variable, the p became an a, but you can also say, I want to instantiate the second variable, and then you write it like that. Then you skip over the p and you instantiate the q with a b. And you can even do things by name. You can say, please instantiate conjunction introduction, and then I don't write the little off here, I write where, and then I can say explicitly where the Q should become B. And here are some examples of compositions of theorems. So we've seen this, of course, that's just an instantiation of the reflexivity theorem. And here, this is the example we just had on the board. And you now see it really gets the only the conclusion A equals A and B equals B. If you just instantiate one of them, then the Q will still be left over. That is in fact what we have there, where we have just one of the two assumptions proved. And you can also decide you don't want to do anything with the first premise of the conjunction introduction rule, so you put the underscore there, and you just want to prove the second premise. And then you get the same thing, dual, where the Q has gone, and it's been proved by B equals B, and the A is the P is still there. And here's just the an application of the conjunction introduction rule now in a backward manner. This was forward from some facts like A equals A. We deduced other facts. Here we're going backwards. So here, if you now apply the conjunction introduction rule, you get two subgoals. One way you have to prove A, and one way you have to prove B, and A and B I have explicitly put in there as assumptions, and so you can apply assumption, and then that subgoal goes, and you can apply assumption again, and that subgoal goes. So if A and B are bigger formulas, then this gets more interesting. Of course, here all of this is in principle automatic. So I've come more or less to the end of what I wanted to talk about today. So I'm happy to take questions about anything that you've seen. Yes?
Where the documentation can we find all the rules we can apply?
In principle, you can apply any rule. I mean, it would be so.
And so the conjunction.
Yeah. Now the point there is that if this were a logic course, I would then teach the natural deduction, and I would show you all the individual rules. But basically, I don't want to do that because this course is not about single-step proofs. I'm just introducing the single-step proofs as a means in extreme situations where you have to take the thing apart. I'm really so the rules that you've seen on the slides, the conjunction introduction, the implication introduction, those are are simple ones that are easy to use, but then there are also elimination rules, and I'm not showing you them as rules. I will show all of these things as proof schemas, where we come to this textual proof language either, where you don't use individual proof rules, but you write little pieces of text, and that's where I want to teach you about these different proof schemata. And I don't want to go to the level of rules. And so basically, they are in some documentation, but I don't think it's a good idea to learn them. I think it's a better idea to look at this, which comes next week, and which has proof patterns, like how do I write a proof that works with a case distinction? You want to prove some formula R, and you want to prove there are two cases, one where you assume P and one where you assume not P. And that corresponds to a certain proof rule, but I don't want to use the proof rule. I want to write some text that is readable rather than just applying some unreadable proof rule. And that's where all these proof rules hide in these texts. Here's another. Here, for example, this is the proof rule that, if you read through it, is quite intuitive. It says we have P or Q, we've proved this somehow, and then from this we show R. How do we prove this? Well, we prove two cases, one where we assume P and one where we assume Q, and in both cases we show R, because we know it must be either P or Q. And so this is, if you write it down as a rule, then this is OR elimination. But please, this is the readable version of it. Other questions? Then the only thing I want to appeal to you is I want to appeal to you to be here next Friday, because this is where I'm going to introduce this language. And if you fail to grasp what this language is about of writing proofs, then you'll have a hard time in the rest of the course. So I know next Friday is after a holiday, but at least I think it is next week, isn't it? Yeah. But I think if you're not here, you'll have a harder time catching up with what's going on. So that's it for today.